In math, we commonly add, subtract, multiply, and divide integers, fractions, decimals, and all sorts of different numbers, including polynomials even. But how do we go about doing those operations on functions? Well, it turns out that it works pretty much the same way. The difference is that we're going to be adding functions together instead of just numbers, or subtracting entire functions instead of just fractions, or dividing functions instead of just polynomials. However, we do have to pay particular attention that once we apply an operation, we also have to find a new domain, because sometimes the domain of the original functions will not be the same as the domain that results once the operation is applied. So if f and g are functions, the sum f plus g is the function defined by f plus g of x is equal to f of x plus g of x. And the domain of f plus g consists of the numbers that are in the domain of both f and g. So we're looking for the intersection of the domains of f and g. The difference, f minus g, is defined by f minus g of x equals f of x minus g of x. And again, the domain of f minus g consists of numbers x in the domain of both f and g. The product f times g is the function defined by f times g of x equals f of x times g of x. And again, the domain consists of numbers x in the domain of both f and g. So as you can see from these definitions, for f plus g, f minus g, and f times g, if f and g are the same, then the domains of those operational functions are going to be the same as well. That's going to change just a little bit when we get into division, because the quotient f divided by g is the function defined by f divided by g of x equals f of x divided by g of x. But remember, we can't divide by 0, so we have to make sure that g of x, that function, doesn't equal 0. So to find the domain of f divided by g, we find the numbers x for which g of x doesn't equal 0 and that are in the domain of both f and g. So the domain of the quotient differs from the domain of the others in that we have to eliminate any values that make that divisor, the g of x, equal to 0. So let's look at an example where we are applying some operations to functions. So let's let f of x equal 2x minus 1 and g of x equal x squared plus x minus 2. And we want to find first f plus g of x and its domain. So remember that by definition, f plus g of x is simply equal to f of x plus g of x. We're told that f of x is equal to 2x minus 1, so we can replace f of x with 2x minus 1, plus we're told that g of x is equal to x squared plus x minus 2. So we can replace g of x with x squared plus x minus 2, and then we can combine like terms. So we end up with x squared plus 3x minus 3. So f plus g of x is equal to x squared plus 3x minus 3. Now that we have found our function, we're ready to find our domain. Well, this one's actually going to be fairly easy, because if we look at the original function, f of x, it is linear, which falls under that polynomial umbrella. So that tells me that its domain is going to be all real numbers. If we look at g of x, it is also linear. It's quadratic, so it also falls under the polynomial umbrella. and its domain is going to be all real numbers. So if the domain of both original functions is all real numbers, then the overlapping, the intersection of those domains is also going to be all real numbers. So the domain of f plus g of x is also going to be all real numbers. So now that we've finished A, let's look at B. Well, notice that B is still using the same F and the same G. The difference is that we are dividing instead of adding. So remember that F divided by G of X is defined as F of X divided by G of X. So F of X is 2x minus 1, so we replace F of X with 2x minus 1. G of X is x squared plus x minus 2. So we replace g of x with x squared plus x minus 2. And we can't actually divide this. If we could simplify, we would. But in this case, it doesn't even simplify. So this would be our simplified answer in this case. Now we're ready to find the domain. Well, remember that the domain of the two original functions are both all real numbers. So that means the domain of our operational function, our quotient function, is also going to be all real numbers, except that what can g of x not equal? It can't equal 0. So we have to take our function g of x and set it equal to 0 so we know what values to exclude from the domain of our quotient function. So it's a quadratic, so we're going to solve it using one of our methods for solving a quadratic. In this case, I'm going to factor because I prefer to factor. If you prefer the quadratic formula, that's fine. It's probably going to take you longer, but that's okay. Set each factor equal to 0 and solve. And we get that x cannot be -2 and x cannot be 1 because both of those values would have us dividing by 0, which we know we can't do. So we have to eliminate or exclude those values from our domain. Again, we have a couple of different ways of writing it. We can write it in set builder notation as x such that x does not equal -2 and x does not equal 1. Or we can write it in interval notation where we would have -infinity to -2, union -2 to 1, union 1 to infinity. Because remember that this means that we're basically including all real numbers except -2 and 1. So in both of these examples, we were working with functions that were originally polynomials and had domains of all real numbers. But let's look at what if we have an example where our original functions are not polynomials. And what we're going to see is that we're going to follow the same process. The only difference is it's going to be a little bit tougher to find the domains just because the domains aren't going to be all real numbers. So let's start by finding f minus g. Well, remember by definition, f minus g of x is just f of x minus g of x. In this case, f of x is defined to be 1 over x plus 2. So we're going to replace f of x with 1 over x plus 2 minus g of x is x over x minus 1. And if we had like denominators or common denominators, then we could go ahead and combine these two. But if you remember back to fractions and rational expressions, you have to have a common denominator in order to be able to combine them. So in this case, we're not going to require you to find a common denominator. We're just going to leave it as 1 over x plus 2 minus x over x minus 1. Now we're ready to find our domain. Well, we have to go back to our original functions and find our domains there. Well, remember that when we have division involved, what can we not divide by? We can't divide by 0. So for f of x, what can x not be? It cannot be -2. For g of x, what can x not be? It cannot be 1. So the domain of f is everything except -2. The domain of G is everything except 1, so the domain of f minus G is going to be everything except -2 and 1. Because remember, our definition said that we're only looking for the x values that occur in both of the original domains. So since -2 doesn't occur in one of them and 1 does not occur in the other, we have to exclude both of those from the domain of our difference. Now let's look at f divided by g of x. Remember, by definition, f divided by g of x is simply f of x divided by g of x. So f of x is 1 over x plus 2 divided by g of x is x over x minus 1. And you might look at this and go, oh, whoa, that's crazy. Well, you're right. So let's rewrite it to make it a little easier to work with, because remember that the division bar is one way of representing division, but another way is the division symbol. So what if I rewrite it as 1 over x plus 2 divided by x over x minus 1? Well, hopefully now you go, oh yeah, wait, that looks like a fraction. So I know how to work with rational expressions when they look like this. So how do I divide? I simply flip the second fraction, or rational expression in this case, and change from division to multiplication. So now what I end up with is 1 over x plus 2 times x minus 1 over x. So multiply top times top and get x minus 1. Multiply bottom times bottom, and I get x times x plus 2. And again, we have to make sure that we eliminate from our domain the -2, which is not included in f's domain, 1, which is not included in g's domain, and we have to eliminate anything that makes g of x equal to 0. So let's come to the side and see, where does g of x equal 0? Well, to find that out, we're simply going to set it equal to 0, multiply both sides by x minus 1 to clear the denominator, and 0 times x minus 1 is just 0. So x equals 0 makes g of x equal to 0. So we have to eliminate the -2, the +1, and 0 from our domain. So this is going to require several intervals. So the first one, we always start at -infinity. We go to the smallest value, which is -2. Union with, start at -2, go to the next smallest value to exclude, which is 0 in this case. Unioned, start at 0, go to our next value to exclude, and then from 1 to infinity. So our domain in this case would be all real numbers except -2, 0, and 1.